Well, this problem talks about a wall, and there's a ball or a sphere touching the wall, and here's the center of the sphere. And at a point above the center, there's a string that attaches it to the wall. Oh, that's an ugly picture. Anyway, it tells you the distance from where the string is attached down to the center of the sphere. This distance, I'll call that D. It also talks about the radius of the sphere. We know that. And we know the mass of the sphere. And they're going to ask us to find the tension in this string and the force that the wall is pushing on the sphere. Well, to help me better understand this problem, I'm going to go ahead and draw a free body diagram. Even though this might be a torque problem, the free body diagram can help us figure out what's going on. So here's the sphere. I know I've got mg pointing downward. I've got the tension, which goes this way, tension, and I've got the wall pushing outwards perpendicular to the wall. I'm going to go ahead and call that the normal force because that's kind of what that is. If I wanted to analyze this, I would bring in my x and y axes. There's x-axis and there's the y-axis. And I see that I had two vectors flat on the axes, but one vector that's slantways. So I'm going to need to find the angle between this vector and this axis. So that angle right in here, that angle, I'll call that theta. Let's see if I can find theta in the picture. It looks like if I drew a line this way, that theta would be right there. The angle between the tension and the horizontal. So you see this triangle right here? Let's redraw that triangle down here and look at it. We've got the angle theta here. Do we know any of these sides? Let's see. This side right here, this side, is the radius of the circle, isn't it? So I'm just going to call that R. This bit right here, this up and down side, that's the difference between the distance they gave you D and this bit here, which is also R. So this side of the triangle is D minus R. So I can figure out what theta is because the tangent of theta is going to be opposite over adjacent. That's D minus R over R. So since I know D and R, I can find theta. Let's go back to the diagram and see if we can figure out what we need to know just from the forces. I mean, maybe we don't have to do torques. That would be nice. From here, let's write the x equation. The x equation, we're going to include this normal force, which is to the left. That's minus n. And that's going to be one of the vectors. And then the x component of the tension is also in the x direction. So it's going to be plus t cosine theta. And this all has to be equal to 0 because it's not moving. I'm going to rewrite that equation down here because it looks confusing up there. Minus n plus t cosine theta equals 0. Now for the y equation, we have the vertical component of t, that's t sine theta, and we have mg pointing downward, so that's negative. And it's also equal to 0 because it's not moving. So the first part, part A, asks us to find the tension, right? Well, there it is. The tension. That's part A. And we know everything else in this equation besides the tension. So I think the tension is just going to be mg over sine theta. And if we calculated theta here, then we can calculate the tension. And we don't even have to do torques. Hooray! Part B asks you to find the normal force. Well, according to this equation here, the normal force is equal to t cosine theta. And if I know t from part A, and I know theta from here, then I should be able to calculate the normal force.